so before we kick off, I just want to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal, of the people of the Eora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I'm so happy to have Jennifer Neal joining us today. So Jen's a geologist with over 18 years experience in brownfields and greenfields exploration, underground mining, mine reconciliation, resource geology, 3D modelling, and seismic interpretation. And she's currently the CEO of Peak Minerals, where today she'll be chatting to us about the work that they're doing to unlock the secrets of the Lady Alma Igneous Complex. So it's going to be a really good session. Please use the chat and we'll open up the floor for discussions at the end. And yes, thanks so much, Jen, for coming on. It's awesome having you.
Everyone can see a screen with some blue rocks. All right, so what you're looking at is, I'm sure most of you already know, we've got some beautiful samples of azurite and malachite there. And of course, these are copper oxide rocks. While we were waiting, I thought I'd just look up just Google azurite just for fun, because, you know, what else are you going to do while you're waiting for people to come online? And I just Googled azurite just for inspiration. And the top questions on Google when people Google azurite is, what does azurite do spiritually? Now, apparently it removes blockages from endless energy points, keeping those vibrations flowing. Didn't know it did that. And also, what power does azurite have? It is apparently the stone of heaven. And how do I know if my azurite is real? Well, it says to break out your Mohs hardness scale and do some specific gravity tests, but I'm pretty sure the people who were Googling the other questions aren't really at a point where they're going to be doing that. So I kind of just thought it was really interesting that people look at azurite in that way and use it. And it goes to show that, you know, even though we've got these rocks have gone back, they've got this huge history and in our culture and in society for more than just being economic like they are. So I'm going to talk about Lady Alma Igneous Complex, and it didn't say we'd solved it. We hadn't unlocked all the secrets. We're learning a lot more than we did a year ago. And I just want to preface this by saying a lot of the work was done prior by Barbara Duggan, who was our chief geologist. She's just recently resigned in order to spend a bit more time at home. So if you're looking for a really good consultant, she could definitely help you out. So I'll just go back and, you know, look at really the big picture with regard to the where the Lady Alma Igneous Complex sits. We're looking in the northeastern Murchison domain. Probably not quite looking at the camera here, but we're looking at the northeastern Murchison domain. This is part of the UME terrain. So in this northeastern part, we've certainly got a lot of strong deformation. These are older rocks. The greenstones tend to be more PC. And you've got a really high metamorphic grade. So especially where we are, you can see that it's been highly deformed and strong, like granulite facies rocks. So as you can see here, we're zoomed in a little bit. We've got this Lady Alma Igneous Complex. It's part of the Malign Suite. So if we go over, you know, where the hell is the Lady Alma Igneous Complex and what is it part of? We've got 4 kind of autochthonous greenstone belts that were deposited around the same time. And during this time, so the Nori and the Plowd, they're all really closely related. I'll put the time scale up there, 28, so over a 250 million year period. So you've got 2980 million years. And this is kind of like, these dates are always kind of a bit, you've got to chuckle, because sometimes when you look at geological timescale, geologists don't look at things in the same way other people do, and what's give or take 20 million years between friends. So when you say the Nori greenstone belt and the Palal, you know, were deposited about 20 million years apart, there's going to be some overlap of these things. And during this time, these mafic, ultramafic suites were intruding as well. So you've got the Malign Suite, which kind of generally, you've got rocks all the way down from Windermere, all the way up to past Meekatharra, really. I mean, that map actually doesn't show the extents where we think we found Lady Alma Igneous Complex. So part of that, you might have heard of the Windermere Igneous Complex, which is the larger one. I'll just check that I can point to it. So further down, so you've got the larger Windermere Complex, which is more traditional. If you look at it, you've got things like the Bushveld. It's kind of given those analogies to, it's a larger system, and you will get more layering. You'll see more traditional layering of like a magmatic sulfide complex. And then as you move over, you've got these large regional structures, these deep, probably tapping mantle structures. And you start getting things like the Atlee Igneous Complex. You've got the UME, the Barrenby up top, and everyone always makes fun of how I say that. So if I say things wrong, you can chuckle to yourself. Maybe it's just a big joke on me, the way I've learned to pronounce things. And then as you get further up, you get the Lady Alma Igneous Complex. This has been recognized for a long time. Further to the north, this is where our project area is. We've done a lot of work in the area, and just through magnetics initially have just gone and inspected some things further to the north as you get into the Flel syncline. And just we've got pretty good relationships with the neighbors, and we said, can you show us your rocks, as you do amongst friends? And we've kind of looked at the rocks and been, without having done the chemistry on them, they look very interestingly like they might be related to the Lady Igneous Complex. So these time scales are a bit. So if you don't like the way I've displayed it, the reason I display it like I do is because I really do think with timing is everything, and timing can be a 20 million year period can make actually quite a bit of difference on how your mineralization is formed and how it's been deformed. So you know, you could put the more traditional, people like to look at these time scales in this format, and that there's nothing wrong with that. It's just, it's not quite as easy as these, as most people know, it's not quite tick, 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 tick. These things happen concurrently. And you'll get a lot of these igneous complexes probably happening at the same time. And we think this kind of represents this large igneous province. So there must have been this huge melt going on. And when you think about it, this chamber down here, if it's been responsible for all these intrusions throughout that 300-kilometer area, potentially even larger. I mean, this is a huge province. So you've got your more Windermere, just shows these fingers of God, as we call this diagram. Barb came up with this diagram, which is it's quite telling. And look, there is a bit of a time break, a bit of a break there. But you've got the Windermere more layered, and then you've got your longer lived kind of these fluids are kind of shooting up, and they're shooting up these structural breaks or these other regional structures. And in particular, where we are with the Lady Alma complex, we know there's quite a substantial regional structure that has undergone quite a few periods of deformation and quite a bit of change. And it's still causing some headaches and causing some questions to be asked on our side about the architecture of the intrusions that we have, that we can see and how they're related, and whether they all are one single event or have been broken up by some of the faulting. But really, this acts as like a super highway for these fluids. They come up, they intrude, and they don't come up just once. You don't get one intrusion. Like I always use when you cough, you don't cough once, or when you're trying to get something out, you don't just, you cough up a little bit, but you cough up multiple times, right? So you get the first bit out, and then you get the second bit out, and it just keeps going, right? And you really got to get the good stuff out at the end. So as disgusting as that is, it's kind of the truth is you start to get some of the good things coming up at the end, which might be your nickel, copper, platinum, palladium, and your cobalt and things like that. So if you look at a more traditional style, this was taken from a paper on Windermere, but this just shows like your typical staging chamber, and you've got this feeder zone, which brings up this melt, and then you can have the more traditional layering where you get vanadium, titanium layers, chromite within it. And so certainly our neighbors over at the AVL are seeing a lot of these chromite. They're starting to see these layers, and they're kind of like, oh, okay, there is quite a bit of layering here. And of course, they're looking at vanadium. There's quite a lot of vanadium in the system. So this is really interesting when you look at the timing. I'll just go back. Yeah, so if you look at this larger map here, you know, to see that you've got all this system, you know, nickel, copper here, vanadium, titanium at Windermere. As you move up into this belt over here, you've got copper. I've just kind of been looking through some of Cyprium's work that they did in the last couple of years, and I actually hadn't realized that they'd found PGEs and they had cobalt, which is really interesting because there are some things we're starting to figure out over at Lady Alma that I can't really talk about yet, but are starting to look very interesting. So where did the copper come from? There's been copper all over the ground. I think there's a lot of people have told me over the years they've worked in that area at Lady Alma. And you can see copper, the one thing about copper is, if you're not aware and you're more of a gold person, copper likes to travel. It's kind of like that old adage, like gold goes where gold wants. Well, really copper does, and as well. And people will go nuts looking for copper because they'll see it all over the ground and think, oh God, there's got to be some really close to the system. Well, no, copper can travel a little bit further than that. It's more your nickel that doesn't travel too far from the source. You might get it up to 1 kilometer. You're probably pretty close to the system if you're starting to see more nickel, which once a little bit of work was done and more thorough geochemical sampling was completed over the area with full geochemical analysis and looking at all the different elements, which was really useful. But we also picked up that there was more nickel in with sulfur than we originally would have thought, which is great because even though there's still a lot of copper, you know, starting to see that nickel come in kind of shows the system is quite enriched. Historically, it's been looked at as a VMS system, and this isn't surprising. I think there's definitely some VMS signatures further to the north. The environment's right for it. You're looking at kind of like Back Arc Basin, that kind of thing. As you travel further down to the south towards where we are, there certainly was VMS looked at historically, but I think what was confusing the messaging was that, you know, you had this large intrusion, and there was a lot of gold in with the copper, and that a lot of that gold came later. It came as part of these D4. I would associate it mainly with the D4 structures that we see on our tenement, which is pretty interesting, and it is difficult because if you've got a system with like these multi-element systems, you typically will get gold with cobalt, with platinum, palladium. So you will see this gold increase. So you have to be very careful that your gold, where your golds come from, and when we look at it. So we haven't drilled for the gold. There's no reason not to. It's a very valid target, but it certainly has distracted people from targeting the magmatic sulfides correctly. And because of the higher element of copper that has been seen on the surface, this is yet another reason. So we've currently on the property, there's larger intrusions, which is our Lady Alma, our Lady Alma, Murchison, and our Copper Hills intrusions. But within those, you know, there's certainly smaller intrusions, and these systems can be very small. And we expect there's many more intrusions, and you will get dozens of them. But out of 100 intrusions, you might get 1 or 2 that are mineralized. So this isn't, you know, you're not gonna, just because you found a mafic gold, it's like kimberlite pipes. Just because you found a kimberlite pipe doesn't mean you have diamonds. Same with magmatic sulfides. Just because you have mafic, ultramafic rocks and you see a layering doesn't necessarily mean you've got all the ingredients to make a sulfide deposit. I've just stopped because I'm not sure if I've bored you all to death yet, but And I'm not just trying to do a cheeky plug for my company. It's not that. It's about bigger picture and thinking outside the box. And I really enjoy a puzzle. And geochemistry isn't certainly my background. I like to look at structure. I like to look at bigger picture type things. But I remember as a student at Laurentian University in Sudbury, it was just a normal day. And the prof came in and kind of said, where did the mineralization come from in the Sudbury Basin? And of course, everybody was pretty quiet because no one likes to answer questions, especially ones that clearly are setting us up for a trap. So as usual, you know, we start seeing them draw out on these old projectors. I put a little inset there for some of the younger people. These were how we did all our lectures on these amazing projectors with a little plastic piece and the a bit of not paper, but anyway, a bit of plastic, and they would draw, the professor would draw on it. And so he draws out a little bit of a trace of the Sudbury, the SIC, the Sudbury Igneous Complex, or you might say the impact structure. It's really up to you. So he draws it out. And, you know, you've got your offset dikes, which were part of it. You've got an impact structure. It's meteorite is, you know, hit the ground. It's caused these breaks, these fractures. And of course, these fractures are filled with some of the melt. And these are some of these offset dikes. So then he doesn't say anything to us the whole time, draws it out, and then does this. He flips it. And he just simply said, don't just accept things the way they are. And then that was it. It was the naughties equivalent of a mic drop. An early naughties, I guess it was probably back in 2000, 2001. And of course, we know this isn't true. We know that these offset dikes aren't feeding the whole system. But it was just that moment where we kind of sat there as students questioning everything. So rather, you've been told this for a couple of years now, how things are, the way they are, and you just accept it. You read the papers and you accept what people say. But, you know, looking at evidence, did we actually go out and look at the evidence? Did we actually see it for ourselves? Or are we just sitting in a classroom and then being very high and mighty when people put out really interesting ideas? So I think it's really good to step back and look at things where you say, oh, that's not going to be economic, the sulfur values aren't high enough right here. And it's like, whoa, there are plenty of magmatic deposits where you've got pretty low sulfur values actually. So, you know, it's kind of like, you just got to step outside and look at the evidence a bit more closely before you walk away and discount things. So I guess what really sprang to mind, because have a close association with Ontario, was when we were looking at it, or when I was getting presented this idea about what this is, we started thinking that it was a bit like Eagle's Nest. So Eagle's Nest was Noron, it was one of their projects. And there was a lot of similarities there. And this area is called the Ring of Fire. I mean, I learned about it in school. It was really up and coming at the time, lots of exploration going on through this McFalls Greenstone Belt, McFalls Lake Greenstone Belt. And what NORAD found was that they had a number of intrusions as well, very similar to what we're seeing around Windermere. So if you think, you can kind of compare the Windermere complex to more Thunderbird here, where you've got your larger intrusion with vanadium, titanium, magnetite, and you've got that layering, and then you have chromite as well. And then, and as you move through, you got smaller kind of intrusions along structures and along this greenstone belt. And you can kind of make some comparisons. And when you get down to Eagle's Nest, it's really interesting to note, most people don't realize that even though, you know, Wiley paid a lot of money for it, $616 million Canadian. I mean, these things are very economic. It's only a couple 100 meters in size, this intrusion. In fact, it's only about 75 meters wide. And the mineralization itself is very small. It's tens of meters, but it goes down to a depth of well over 1,500 meters, or at least I think, right? So these systems are, I think Steve Beresford talks about this too. I mean, there's quite a few deposits worldwide, these intrusions worldwide that are economic, that are quite small. And you wonder why we keep missing them. You wonder why we think everything's already been found in the surface. We think it's going to be easy. You just do an EM survey, electromagnetic survey, and it should just come up really easily. Well, that's not the case. Most magmatic sulfide deposits weren't found right away through this method. So you need to keep a very open mind on these things. And this was a lot of hard work. People see an overnight story, but this is 20 years of hard work by the guys at NORAD trying to get this developed. So we've kind of always thought that we're on the copper end member where we are, just because of the amount of copper, and we do see magmatic, there's veining, copper veining. It's not just all remobilized within shears and within faults. There was some evidence that past drilling, and if you can do the statistics on it, and you do see two very clear populations starting to separate out when you look at the Copper Hills area where we are. So it gets you starting to think, how are these things economic? And most people don't know that some of the largest, the largest copper deposit, there's Volkovsky, there's Suka. These mainly consist of copper. We don't have a lot of nickel. The ratios of nickel or copper to nickel are copper is quite high. And anyway, so I think within the copper end member, you're dominated by these zones of magnetite, which we see a lot of magnetite around the system. It can make things very difficult when you're exploring. And what we don't see where we are is vanadium and titanium, or very high amounts of titanium. But we do see that with our neighbors who aren't too far away. So we do see the relationship in the system. And because of how copper moves, I think people do forget about it. But we think with the prices the way they are of copper, and the expectation that in the next 50 years we're going to be short, substantially short, even in the next 10 years of copper to meet all our battery needs. Investors are very excited about even small amounts of copper at the moment. But these systems have always been interesting. It's nickel, these copper nickel systems have always been highly profitable. So we'll just move on. I spoke briefly about some of these examples. You've got Sakati, which again is a very small intrusion hosted within peridotite, very similar to what you can see over at Lady Alma. We do have peridotite and peroxenite within volcaniclastics. Within volcanics. And we're looking for our massive sulfides. They've already found theirs, which is great. And there's quite a few other deposits, mainly in Russia and Finland. So there is a lot, and we certainly don't have all the information we'd love to have coming out of Russia. And certainly I know I'm not as across it as maybe Barb is, who's done a lot of the legwork here. But yeah, it's you look at the copper nickel cobalt ratios, and that's actually not too dissimilar to what you see where we are. And that's just, again, the copper sulfur ratio showing that copper is quite high. But what happens is as you get further down, deeper into further down in the deposit, the nickel starts to increase. And so that copper nickel ratio changes quite substantially. I have looked at a talk by Steve Beresford a little while ago because I just wanted to, it was quite a long time ago, but I looked at it again recently because I really liked this image that he did, and it's so simple and it just tells the story perfectly well. And I highly suggest you watch the Steve Beresford presentation because it is a good drinking game if you want to use the word lapis lazuli, if I said that right. But I highly suggest that you have a go at it for all the uni students out there, or you young geos. You can get pretty far on it, I think. And so anyway, looking at this primary footprint, I think it just drives home these kind of this alteration halo. You got the distal footprint, which can be quite large. You've got exogenic veining on the outside or on the peripheral of the deposit area. Within this chonolith, which, you know, you've got your igneous, your mafic, ultramafic, or your host rocks, and then you get more disseminated net textured mineralization and your massive sulfides somewhere in there. Hopefully you found them. If you're like us, we haven't really got there yet, but we're getting much closer. And this is kind of an example of what we're talking about. When you see this is the Aster Imagery. You can pull this straight off GeoView for all you explorers who are just starting out. So there's great government data out there, but this is the aluminum oxide footprint from the Aster data, and that's over the whole. You can see the outline in purple of the mafic, ultramafic, the main intrusion. This is a very simplified version of it. But then with that, you can see the opaques, and that shows a very, very clear ring. And these stars are observed copper. So these are all the rock chips. And these are quite high copper, 22%, some of them 14%, like a lot of them are above 1% copper. So there is quite a lot of it, but it is showing that there's a clear outline. And it's mapping it really nicely. So you can use very free government data to understand the true extent of your alteration halo. And that's not too dissimilar from what we were seeing here with the size of that halo. Other things that kind of you start to see at Lady Alma, which we're seeing, and we've kind of now documented more with further drilling and hope to do a little bit more of very soon. You get this exogenic veining, or some of these magmatic sulfides that have shot out from something potentially quite large. This really is the goods. You've got your chalcopyrite, we're seeing bornite. We've done SEM work on this and seen that we've got this three-phase sulfide system. So you got your pyrrhotite, your pentlandite, and pyrite. And we're also seeing a bit of millerite as well, which confirmed that. We kind of suspected it by looking at the core, but didn't want to jump to conclusions, and then did some of the SEM work and the petrography, and were able to confirm that millerite, which is quite funny because one of the old timer geologists came into the office not too long ago and looked straight at the core and said, "You've got millerite in your core," and he was dead firm on it. Whereas, you know, we tend to be a bit more reliant on the old school systems and on the new system, by always having to have the chemistry and always having to have this additional information and not trusting, you know, your eyes and your senses, all your senses. I'll just quickly, one other thing is some of the work that Barb was doing by looking at the chemistry was actually really important, because these rock chip samples here were taken all around. Not all of them are shown, but the ones that were separated out, you can see she's done the chemistry by looking at, you know, magnesium content and chrome, and some of the other elements, and working at the ratios. She's been able to kind of categorize or classify these as from primitive to more fractionated, less primitive. You know, like, it's not all going to be perfect because there are a lot of other things going on in the system. But what came out of it, which was really interesting, so this is done independently, is that there was this grouping of more primitive samples on one side, and certainly more fractionated, where we know we've got gabbros coming in. So you do see within these magmatic sulfide systems, you know, go from your primitive and more with your melts, sorry, your primitive rocks. So you get more your prototype peroxenites, and then moving up into your more fractionated, where you get your gabbros. This is really simplifying it right now, sorry for everyone, but into your more fractionated rocks, you'll have your gabbros, or into your more felsic rocks, and which we do see quite a bit of layering down further at Copper Hills. So this Chonolith and igneous architecture that Steve Beresford mentions as well. We kind of had a theory, and the theory was just based on some of the mapping that was done, as well as confirmed with some of the geochemistry, and just coming up with an idea. Sometimes geologists forget the simple art of just coming up with something, and it doesn't have to be perfect. It doesn't have to, I know everyone thinks it's the end of the world if you're wrong, but it's just come up with something, a working model, test your theory. And that's the most important thing, because we have to fail to move forward, or we have to, in order to be successful eventually. So what we did was we've come up with a model. I mean, it's pretty reasonable for the most part, but it just shows us and gives us a good visual indicator of where we're drilling, what we're doing. And every time we get a new piece of information, whether it be a VTEM survey, reprocessing of excite, or magnetics, gravity, you name it, you just kind of tweak the system over and over again. And that's what good geology is about, is knowing when you're wrong and tweaking your ideas. And that's pretty valuable. So one of the things also that made this really interesting is that we were able to see the timing, which surprisingly people hadn't really seen this or documented it before, but you can see that you've got these margins of this intrusion coming up, this ultramafic intrusion. It's got malachite in it, and it's intruded into the dunite intrusive host. So you've got multiple intrusions. This is proof we've got these timing relationships here, where you've got the dunite has intruded into the greenstone belt very, very roughly the same time. And then this has come through. So there must have been some, some cooling that had occurred before this had intruded up. It's obviously come up a shear, inundated this shear zone, and come up and intruded into the host rock. So there is quite a bit of evidence of that, and it's interesting to see. And when you talk about timing, this is a great example. So we hope to find a few more. In some samples in core, you can see that the chill margins aren't very particularly strong chill margins, which suggests that one wasn't quite cooled before the other, obviously. And anyway, so it's quite interesting. So when we look at the disseminated sulfides in the core, I pulled something from Eagle's Nest. I'm not saying we're similar to Eagle's Nest. I'm just saying, like, the textures, it doesn't matter where you go. You can look at, and I've done this before with gold greenstone belts. You can look at the rocks in one country and go to another, and they don't look too dissimilar because the systems behave in the same way. So, and this is Our Lady Alma core. Got disseminated going into kind of net textured sulfides with chalcopyrite and pyrrhotite, so these interstitial chalcopyrite. And through here we've got within the peroxenite, you've got magnetite, pyrrhotite. Again, which this magnetite in the system is quite strong, and copper as well. So it's just showing that relationship and between the two different deposits or two different prospects, and all these similarities. But we do have this disseminated mineralization. So where is the more massive mineralization is the question, and that's what we're grappling with right at the moment. But every time we drill a hole, we get a little bit closer, and using good, using chemistry and just good old-fashioned geology and tweaking our model, we're kind of making some leaps and bounds. So, and I think the key, as well as some advice from a friend at Weiler Metals, just said, don't give up on these things. If the system's got what it takes, you don't give up, and just keep doing all the good work. Do the SEM work, do the petrography work, your downhole EM, just keep pummeling it every hole that you drill. So this is a good, coming from a bit more of a seismic background. It's been a while since I've looked at electromagnetics as much as I have in the last year, and magnetics, and going through and having them reprocessed. And one of the really frustrating things is you see companies will have this nice red, highly conductive target and drill it and come up with massive sulfide. And that just doesn't happen all the time. I mean, most, as a said, I think Steve Beresford said in his talk, is you don't necessarily get most magmatic sulfides don't have a signature on the surface. Mainly, there's a little bit to do with depth, because a lot of this is disseminated mineralization at the the surface, and so you'll see these showings of mineralization, but it's deeper that you need to see, and a lot of these techniques aren't really good below 300 meters. So here again is just a V10 model and showing some really interesting. You can kind of imagine that maybe there is some disseminated sulfide up here, which there is in these holes over here, and it's funneling into a deeper, more massive set of more massive mineralization, which is kind of the hope with these things. So you need to really be in that sweet spot of 300, and obviously if it's quite substantial, you probably see it with moving loop EM, some of these ground techniques. But I think what's really interesting is coming from, again, that seismic background. I didn't really ever want to look at seismic when I was doing my master's degree. I did want to get into more traditional things that I haven't looked at in a while, like EM, and apply it to the mineral system. And when I was kind of put onto the seismic at Kivitsa, doing my work there, I wasn't totally sold, but then as I did a bit more work, it became really interesting, because you could clearly see the layering in the intrusion using the seismic. And I think moving into high size and doing some of the work with them, got to see dozens and dozens of projects and examples where it does work. Sometimes it's not as clear cut as others, but for example, the work at IGO with the Nova I, this, I can't obviously show any of the work I did, but it was pretty clearly outlined the eye, and was very useful in targeting some of the newer intrusions such as the Lara, Aries, etc. So can be quite useful. And the good thing about seismic is that sweet spot is actually below 300 meters and down to a depth of about 2 kilometers, but it's extremely expensive. Certainly when you get into the Windermere complex over here, you're looking at a depth of this 5 kilometers right here. So to get into the more, which is probably why at Windermere you haven't really found that highly that big deposit, is because it is going to be quite deep potentially, unless it's being trapped in some embayments or in structures. In here, which you see at Canegrass, there's some pods of mineralization caught up in shearing. But these are the kind of depths you can look at with seismic. And this is from Legend. They did a 3D survey, and they were pretty chuffed when they saw this result, showing the extent of the that contrast between the host and the Mawson Chonolith. And every time I talk to geologists, magmatic sulfide people, they don't care about faults or structure, other than the fact that, yes, we know we need a deep mantle tapping regional structure, and that's just not the case. I mean, obviously, yes, you do need, in order to get some of these, they have to intrude usually up weaknesses in the rock. You can't just have it, there'll be an intense pressure, which is really important to these things, but also they will need to eventually inundate a structure and come closer to the surface. But what's really complicated the picture at Lady Alma and Brixton is that there is, and you can see just how significantly deformed these intrusions are. You get your very classic kind of like eye-like feature in here, but then wait, we've got another one over here, and it would look, but for all intents and purposes, that this larger shear zone, which we think is probably where all the fluids have come up, because this is a very early structure. It looks like they've been offset just by a quick glance, but then the motion, the movement is actually quite the opposite. So it must have undergone multiple periods of this reversal from dextral and sinistral. So it's very, this is a Proterozoic dike. I always just call them pods just to confuse people, but Proterozoic dike, and you can clearly see it's been shifted or moved. And was that from the fault? And that's why we're a bit confused, or is it from something else entirely? And given that these are quite late compared to everything else, it does, you've got to ask a lot of questions here. What's happened with the intrusion itself? Definitely, I've talked about these D4 structures. They're quite simple. They're the ones that kind of, a lot of the gold you find, which is a later overprinting event. We do see quite a bit, up to 15 grams per ton gold in places. It's not in targeted because it doesn't always hold together, but then again, we haven't specifically targeted the gold along these structures to this point. So there is always more to look at here. It's not a simple thing. So I think one of the things we're starting to find is there probably has been quite a bit of thrusting, not only in the more obvious from the compressional event that occurred along that, so that D1 structure, you get isoclinal folding during D1 and D2, which is so periods of compression and extension. And then you get these later kind of creating east-west or northeast folding during D3. And during this time, there would have been more thrusting. And so some of these would have popped up, and potentially Copper Hills might have, gone down. And then, on top of that, there's this late cross-cutting faults again. So it is very complex and very important, because if some of this movement, reverse movement is hundreds of meters, this can make a huge difference to why we might not be seeing as strong an EM response over down at Copper Hills, even though we can clearly see there's a lot of mineralization there. So again, follow the recipe. There's lots of great stuff here. Deep mantle tapping structures, this geometry, and this igneous mafic ultramafic intrusion, and kind of sulfur saturation. There's the presence of magmatic sulfides clearly, and really what we're just looking for is more economic mineralization. And this is really important to us because not only obviously as a company we want to make the next big discovery, but I think the next big discovery could open up the whole Windermere, like that whole system of malign, sweet, mafic, ultramafic intrusives throughout. And when I spoke about seeing some all the way to the north, near where Great Boulder was at Sidewell, and over to the western side, where the mica metals are, we're seeing, you can see a lot of unclassified mafic intrusions that have come through. You start to question the extent of this system. Where is the next big massive sulfide deposit in the air, and is there going to be one in this area? And if it does, will it open up the whole area? And I think it's a great opportunity to keep moving the work ahead. And I don't think there's quite as much, considering that it's pretty easy access from Meekatharra. I would like to see a bit more work come out of it. So anyway, that's me. I'm sorry if I butchered some of Barb's work, and I didn't talk about the chemistry certainly, but that's not my expertise. So the chemistry, I assure you, if you have any questions, you can talk to Barb Duggan, who is principal geologist.